So moving on to uh, the next example here. Again, we want to evaluate this integral. It's not a standard integral. So we want to look to see if we can apply our substitution to this integral. So looking at this integral, we want to try to identify an inside piece. And this e to the x appears to be kind of more on the outside. So if we look at some embedded piece here, this would be the more obvious choice. So 1 plus e to the x. So we're going to try that, and we're going to let u equal 1 plus e to the x. We take its derivative, du by dx is equal to the derivative of e to the x itself. And again, we'll move that du divided by dx, and we'll put the dx on this side as a multiply expression. So then it looks like then this is exactly what we really wanted. We wanted to be able to have the derivative of the inside accommodate the leftover outside piece. So it looks like it's going to work here. So then I'm going to rewrite this integral. It's going to be the integral of, and I'm going to write like this, square root, the inside expression, u, okay, and the outside expression I'm going to replace with a du. Okay, and there we have it. Now we have an expression in terms of u with integrated with respect to u. So this will work. So we now can integrate this, looking at this as a power rule. So I'm just going to rewrite this as u to the negative 1/2 du. We're just going to apply the power rule here. So we're going to increase the exponent by 1 and adjust for that coefficient. And then we have a plus c. So I'll rewrite this, just simplify this a little bit. We're going to end up with 2 root u plus c. Again, we want to replace that u with some x expression. Well, there's our u. That's in terms of x. I'm going to replace it with 2 square root 1 plus e to the x plus c. Okay, and we can check again. Okay, we're going to check this expression. If I differentiate that integral expression that I generated, it should give me back the original expression. So I'm going to differentiate 2 root 1 plus e to the x plus c. The derivative of this is going to end up being 1 over 2 square root. Okay, there's our expression. I have an embedded function, so I need to apply the chain rule here. So times the derivative of the inside is e to the x plus 0. 2's cancel out. I end up with e to the x 1 plus e to square root e to the x. There we have it. We end up with what we started with. This must be the right integral then. Okay. Looking at the next one here, if we take a look at these pieces here, we have to decide what is the inside piece and what's the outside piece. There's actually a choice here, but we're gonna use the more obvious one. Okay, and if we look at our integral or derivative charts, we know that the derivative of tan is going to be, well, this is not going to be quite the right one. So we need to kind of take a look at this and evaluate this and figure out what would be the best function where the derivative of the inside is going to be the outside expression. Okay, now we probably can rearrange some of this expression, and it's going to look like this. So if we think about any trig functions, they all can be expressed in terms of sine and cos. So if I rearrange this into sines and coses, I end up with 1 over sine squared x times sine cubed x over cos cubed x dx. Now, if I simplify this expression, what ends up being nice about this simplified expression is, on the outside, I have a sine x dx. And this sine x dx, we know, can be expressed as a derivative of that inside cosine function. So here we're going to let our inside be our cos x function, and then we're going to let that derivative of that see if we can generate this sine x dx, which it will. So I'm going to let u equals cos x, okay, not cos cubed, but cos x. Now the derivative of that u is going to generate our sine function. Okay, and we can, that negative is easy to deal with, it's like a coefficient, so I'll just put the negative on the other side here, and there is our sine x dx that we wanted, that we need to do our substitution. Okay, so this is going to match this part of our expression here. So rewriting this then, my new integral is going to be the integral of u cubed, and we're going to replace the sine x dx with a negative du. Okay, so now we have our integral again in terms of our variable u with respect to u. We can apply power rule here. So I'm going to just rewrite this as u to the negative 3 du. Using the power rule, I'm going to end up with u to the plus 1, so negative 2, divided by negative 2 plus c. And again, we're going to replace that u with an x expression, which the u was equal to cos x. Oops, sorry. U is equal to cos x. So then the negatives cancel out. I'm going to end up with u is cos squared x plus c. So there's my integral function once I plug that all back in. Again, I'm not going to check this one, but again, you can check these and test these to see if when I differentiate this, I'm going to end up with my original integral expression. In this case, it's here. So this one's slightly different, and we need to do some algebraic rearrangements. There are some other choices of substitution that we could have used, which are a little bit more complicated, but they will all work if you can use some sort of substitution here.